Hello children, welcome back. So in the last sessions we understood about the force acting on a charged particle which are moving in a magnetic field, and also we understood what is the trajectory of charged particle inside the magnetic field. Now this session we will continue with the force acting on current carrying conductor. Let us do that. The force acting on current carrying conductor. So you all know that what is the formula? Current carrying conductor. Let us suppose there is a long current carrying conductor which is carrying the current I, and its length is L, and it is kept inside the uniform magnetic field B. Now the angle between length and magnetic field is nothing but theta. Then the force experienced by current carrying conductor is given by the formula I into L cross B. I into L cross B, and the magnitude of the force is given by BIL sin theta. So from here what we can understand, if theta equals to 0, what is the meaning of it? If the angle between length and magnetic field, what is that? If the length of a conductor is parallel to the magnetic field, then the force will be F sin 0 equals to 0, so force will be equals to 0. And if theta equals to 90 degrees, then the force will be the maximum, which is nothing but BIL. Now let us see some special things related with this force acting on a charged conductor. Here I told about the force acting on a charged conductor whose length L is a straight line. So let us suppose I have some arbitrary shaped conductor. So let us like that. Let us have one arbitrary shaped conductor which is in the shape like this. I have uniform transverse magnetic field, and here there is a one conductor which is in arbitrary shape like this. Let us suppose this is the starting point A, this is the ending point B, and this is the carrying I. And what is the direction of the force acting on a charged conductor? That will be given by Fleming left hand rule. What is the Fleming left hand rule? The forefinger shows the direction of a field, the center finger shows the direction of a current, and the thumb shows the direction of a force acting on a conductor. And so let us come back to this one. So here what I told, it's a uniform magnetic field. Within that one conductor is there, and it is called as an A and B. It is some arbitrary shape, and it is carrying the current I. Then what is the force acting on it? The force acting on it is nothing but BI into the length of AB. That means if I join the straight line from initial point to final point, then I will have a one perpendicular length, one straight line. That length is nothing but LAB, and this LAB is called as a effective length of a conductor. Effective length of conductor. Effective length of conductor. Right? So let us see one example so that you will better understand this. Here I have one example for you. There is some transverse uniform magnetic field whose direction is into the plane of a board, and there is one conductor which is in a semicircular shape, and let us call its radius is small r, and it is carrying the current clockwise in the clockwise direction, and we would like to call this conductor as a AB. Now what is the force acting on this conductor? As I told you, if the conductor is in some irregular shape, then we have to calculate its effective length. Effective length is nothing but the length of a straight line joining the initial to final point, and this is nothing but double of the radius. Therefore what is the force acting on this conductor? That could be written as BI into the length is nothing but 2R. This is going to be the force acting on this conductor. What is the direction of the force? The direction of the force is nothing but, let me use the Fleming left hand rule. What is that one? The forefinger shows the direction of a field, so it is into the plane of a board. The central finger shows the direction of a current. This is the direction of a current. Then the thumb shows the vertically up. Therefore the force will be vertically upward direction. For suppose if that vertically upward force is balanced by the weight, then it will be remain there. So it will be under equilibrium whenever Bi to R equals to mg. If I think its mass is m, then it will be remain in equilibrium when Bi to R equals to mg. This is the concept. So whenever the conductor is in some irregular shape, we need to calculate its effective length. With respect to effective length only, we could calculate what is the force acting on a conductor. Well, shall we go with some more illustration? Well, see here now. Here, let us suppose there is a uniform magnetic field, and within it one conductor which is in the shape like this, and let me call it as an ABC, and this is an AC. Both are carrying the same currents, I and I only. Like this, it is carrying the current. Now, what is the force acting on it? Here, two conductors are there. One and another one is 2. Its effective length and its length both are same. Therefore, what I can say, F will be equals to B into I into 2 times of AC. 2 times of AC. If I think its radius is R, then what I can write? B into I into 2 times of 2R. This is going to be the force acting on this loop. If it is conducting the current like this, here I have drawn the current is like this. One part is going this way, one part is going this way. If I think the current is going as a closed one, then what will be happen? Then this what will be happen. See this one. See this example. I have uniform transverse magnetic field. So here I am giving the 2 examples. Well, so in this field, let me assume I have a circular shaped conductor which is carrying the current I, and in this magnetic field I have some arbitrary shaped closed loop. Of course, it is also carrying the current I only. Then what are the forces acting on this? For this, the force will be equals to 0, because effective length for a closed conductor, closed circular shaped conductor will be 0, therefore force will be 0. Then what will be happen for this loop? So it will begin to stretch. Whenever you keep this kind of arbitrary shaped conductor, then it will begin to stretch in such a way that it will become a circular shape. Until it becomes circular shape, the force will be acting on it, so that finally it will be remaining in equilibrium, having force equals to 0. I told you here, for a circular shaped conductor, force will be 0. If you keep any arbitrary shaped conducting loop, a closed loop, that may be in any shape, if you keep inside it, then it will be stretched to become a closed loop. Then I asked you here one question. What is that? If the current is splitting here like this part and this part, what will be the force? This will be force. If the current is closed here, then what will happen? Even this one also it will compel to become a closed loop having different radius than this. So it will try to become one different radius, the circular loop. In that way it will become, so that the force will become 0. It will be under equilibrium. This is what will be happen. So hope you understood all these things. So what I have covered here, I have covered the force acting on a current carrying conductor, and that is given as a BIL sin theta, or maximum force experienced by the current carrying conductor is given as a B into I into L. So you understood all these things. Well, now we will go with some numericals. Let us start now. Well, so look at this problem. So here I am writing problem, a rod of length, a rod CD of length B is carrying a current I2, is placed in Well, so here is the diagram, and so let us try to understand this. So a rod CD, this is called as a CD. So a rod CD of length B is carrying a current I2, is placed in a magnetic field due to a thin long wire AB. This is a thin long wire AB which is carrying the current I1 as shown in figure. Then find the force experienced by the wire. How much force will be experienced by this one, that we have to find out. See, let us see now. Listen in a magnetic field. Well, see this one. So here, according to this given diagram, let me redraw this. So it is carrying the current I2, it is carrying the current I1. Now if you closely observe this one, you can understand one thing. The magnetic field due to the current, the straight conductor is nothing but I equals to, what is that, mu naught I divided by 2 pi r. The magnetic field intensity due to the straight conductor is nothing but mu naught I by 2 pi r. Here B is inversely proportional to R. That means what? If you go away from the straight conductor, magnetic field intensity will be keep on decreases. So here on this point, what is the magnetic field? That is different on this point. That is different from here. And it will be completely different from this value, and this will be the least, this will be the maximum. The magnetic field intensity is maximum at this point, minimum at this point, and it is keep on decreasing along the length. Therefore, the magnetic field is varying along the length. So we know very well, whenever the current carrying conductor is kept in a uniform magnetic field, the force it experiences is nothing but BIL sin theta, depending upon the angle. Now here magnetic field is completely varying from point to point. Therefore, we cannot apply directly that formula to calculate what is the force experienced by this CD. Therefore, what we will do, we will apply the integration technique. So in the integration technique, what we will think is, we will think of one small element here, which is having a width of dx. And let us suppose it is at a distance of x away from a conductor. And we already know this distance is nothing but A, and this whole distance is nothing but B. Like this we have. Now let us try to find out what is the force acting on it. Now the infinitesimally small force can be given by the formula BIL sin theta. Here what is the theta? Angle between length and magnetic field. Length is like this, magnetic field is into, because it is carrying the current like this. So field will be into the plane of a board, and both are perpendicular to each other. Sin 90 equals to 1. Therefore, what we will get? BIL. Okay, fine. What is the B now? B is nothing but mu naught I by 2 pi r. That is due to this carrying conductor. Therefore, what I can write? Mu naught I1 by 2 pi. Here, what is the R? Distance. What is the distance here? X. Therefore 2 pi x multiplied by, what is this I? The current carrying conductor is conducting how much current? It is a current carrying conductor. That's what we kept inside the magnetic field of this one. Therefore this I is nothing but I2. And what is the length? This is a small element dx. So here we try to find out the force acting on a infinitesimally small element of this conductor having the length of dx, and that is given as a df equals to mu naught I1 I2 by 2 pi x into dx. Now what we have to find out? We have to find out the complete force. How to find? We will do the integration. What is the integration limit? Mu naught I1 I2 divided by 2 pi integral x 1 by x dx. This is going to be the formula. Now we have to substitute the limits, right? What are the limits? This x, what is the minimum value? A. This x, what is the maximum value? A plus b. So this x is, we have taken, its minimum value is nothing but A, its maximum value is nothing but A plus b. Therefore the minimum value is A, maximum value is A plus b. If we simplify this, what you are going to get? Mu naught I1 I2 divided by 2 pi times of log x to the base c from A to A plus b, which upon simplification will give you mu naught I1 I2 by 2 pi times of log of A plus b by A to the base c. This is going to be the total force acting on the another conductor, which is kept inside the magnetic field of one conductor which is carrying the current I1. In this way we have to solve this problem. Shall we move for next sum? Well, let us go for next illustration. So here we have another problem. Well, so come to this problem. They have given like, so a current carrying conductor of mass 50 grams, its mass is 50 grams, its mass equals to 50 grams, and it is carrying length 0.5 meter, length equals to 0.5 meters, hanged by two identical springs, each of stiffness K. Okay, for an outward magnetic field, it is an outward magnetic field B. Find the deformation of the springs given that I equals to 1 ampere, the current equals to 1 ampere, the magnetic field intensity is 1 Tesla, and the stiffness of the two springs are 50 Newton per meter. Well, what is the meaning of this deformation? Deformation is nothing but whenever a spring is given with a certain force, let me call it as an F, then due to this force what will happen, it will be slightly come down, and we know that the restoring force developed will be equals to K into X minus K into X. Then this X is called as a elongation taken place for the spring, or in other words that is the deformation taken place for the spring. So here they are asking to find out the deformation. The deformation here is nothing but what is the amount of stretch that is being taken place for the both of them. That's what we have to find out. And see here now, since it is carrying the current I in this direction, what will be the direction of a force? Let us use our Fleming left hand rule. What is the Fleming left hand rule? Forefinger shows the direction of a field. What is the direction of a field? This is the direction of a field, and the central finger shows the direction of a current. So how the current is? So like this it is. Then what is the direction of a force? Vertically downward direction. Vertically downward direction. Right? So therefore, what we can say now, in the downward direction, I have the force mg, the weight of this rod, and this magnetic force, shall I call it as an Fb, which is nothing but BIL, that is acting in vertically downward direction. And in the upward direction, what will be the force? There will be two springs. For the both springs, we will have a restoring force. F equals to K into X. I am writing just magnitude. The restoring force magnitude is nothing but K into X. For both of them, spring constant is same. Even the amount of stretch will be also same. Therefore, what is the total upward force? That could be written as 2K into X. When these two are balances, then it will be remain there. Otherwise, it will have some oscillation. So here we are not interested to understand what is the oscillation which is taking place. Just I am interested to find out what is the amount of stretch. Well, now let me equate these two forces. How? 2kx must be equals to BIL plus mg. This is going to be the amount of stretch that I could calculate. Now let us substitute all the information what we know. What is the magnetic field intensity? 1 Tesla. The current equals to 1 ampere multiplied by what is the length? The length equals to 0.5 meter plus what is the mass? Its mass is 50 grams. So 50 into 10 to the power of minus 3 multiplied by the 10 and whole divided by 2 times of what is the K? 50. Now let us simplify this result. So what will get? 0.5 plus and here 100. So again I will have 0.5 only whole divided by 100. That equals to 1 by 100, which is equals to 0.01 meters. This is going to be the amount of deformation or amount of stretch taken place for the spring. This is how we can do this problem. Well, shall we move for the next illustration? Well, here is the next illustration. right? Now see this problem. Here we have a rough inclined plane whose the coefficient of friction is given as a 0.1, inclined at an angle of 37 degrees, with the horizontal has a metallic wire AB of length 20 centimeter, and when a current I is passing through the wire, the magnetic field is applied normally to the plane, which is in upward direction. The wire starts moving up with a uniform velocity. For given 0.5 Tesla magnetic field intensity and mass of the wire 50 grams, what is the magnitude of the current that has to pass through the wire? That we have to find out. Let us try to draw the diagram first so that we will understand what is happening there. Well, so that will be something like this. So let us assume it is an inclined plane. It is an inclined plane. So let us assume it is an inclined plane, and where this angle of inclination is given as a 37 degrees, and here one wire, they call it as an AB. It is carrying the current I, and magnetic field is applied normal to it, like this it is applied upwards. So this is the plane and this is the plane, actually like this it is applied. You just imagine like, so this is a inclined plane, the magnetic field is applied like this, and the conductor is kept in this way. Now we have to find out how much current has to pass through it so that it will be move up. That's it. Stop it.